Hello and welcome everyone. So now we'll again delve back into the mathematics that we have started. So I'll just briefly summarize what we have seen so far in the basics of linear algebra. Before that, I would love to cover one more thing. So in the mathematics portion, what are we going to cover? Just to remind you. As you know that this mathematics per se won't cover all the topics in mathematics, but this will be just an introduction to the mathematics that is used in the machine learning. So in mathematics, we'll see calculus, and then we'll see optimizations. We'll also see probability and stats. We'll see linear algebra. Okay, and maybe some more topics that are related to these things. So these will be the core things that we're going to cover. That's the plan in this course of machine learning and deep learning. So in here we have started with pre-calculus, in that we have covered functions, and we have done some pre-algebra, so in which we have covered different topics of what a vector is and what these things are. So maybe after this we'll cover these things. So now we're at this topic, okay, linear algebra. So in this we have covered some basics, so I'll just summarize these basics for you, and today's plan is to make you visualize all these things, what we have studied so far in these basics, and I want you to visualize that stuff. So the first thing that we discussed there was vectors. Okay, so we said that there are three sort of people who study vectors. The first was physicists. If there are people from physics, they deal with vectors. So in physics terms, so it is basically more or less application based. There you might have seen people call it, they have magnitudes, the quantities which have magnitude and direction are called vectors. And then there are computer science people, so physicists and CS folks, and then we have mathematicians. These are the three types of people which you will commonly see using these vectors, and they use these things in their own notions. As CS people just call it array of numbers, and mathematicians, as always, they just try to abstract out all the details and say, okay, this is the template, okay, let's generalize it more, and they came up with vector spaces and things like that. So we are interested in these two things more, CS and mathematics perspective. And then we covered what is the position. So this was the thing that we covered. Then we covered position, how to define position, and with respect to that we defined coordinate systems. So I should give a shout out to one of the students, Arshan. He actually sent me the notes which sort of made it easy for me to just see the topics that we have covered. And positions, from that we covered coordinate systems, and then we covered the distance calculations. Once we have the vector or 2 points, let's suppose we covered two types of distance from the origin and distance between within 2 points, and we did it in 1D, 2D till ND. And after that we saw some properties of these things also. So what are the different properties that these vectors follow, and after that we saw vector operations, where different operations that are performed on the vector, like transpose, addition, scalar multiplication, subtraction, and multiplication. In that we saw element wise multiplication, and we also saw dot product, and then we saw projection. This is also an operation, but these are the important things. I'll just, dot product and projection were the important things. And then we also covered decision boundaries. This is what we have covered so far. Okay, so now this lecture is basically dedicated to the visualization part. If somebody speaks about a vector, what should pop up into your head? Okay, and because if you have these visualization intuitions right, then maybe you can build on these foundations and have stronger foundation to create something really nice. Because I feel the way algebra is usually taught is all these equations, all these Gauss-Jordan methods, elimination method, whatever, and people don't know what they're doing. They're taught mechanical way. So I have told you in the initial lectures that we'll see maths from rediscovery point of view, as if that you have discovered it somehow. So we want to discover the maths for yourself. Let's again go back and see the visualization. I'll use a lot of code today because I'll assume that you know all these concepts. I won't explain them much, maybe just brush up, and after that we'll directly go to the code. Okay, I'll bring up the code over here. So the first thing that we'll see is a Cartesian plane. Okay, where is the position? We saw why do we need the Cartesian plane. So it will have an x-axis and a y-axis. So this will be called a y-axis and this will be x-axis, and then we have their origin. This is our origin, and with respect to this we basically measure either a position or whatever thing that we want to measure with respect to this coordinate system. So how to now draw this coordinate system? Okay, this coordinate system, if you see, it divides the whole 2D plane. Okay, and computer screen usually is 2D. Okay, and then we can also use it as 3D, where we use different techniques how to project these 3D things onto 2D. That's a different subject in itself. But here, if you see, our computer screen is a 2D thing, and there you can divide it into 4 quadrants. Okay, and by the help of these 2 axes, x-axis and y-axis. Okay, how? Let me code that and let me show it to you. Going to the code, and I should take this over here and bring the mouse. I hope you are able to see the screen. Okay, so you know how to define a position in the coordinate system, because to define position we need 2 values, x value and the corresponding y value. I don't need to remind that. I think that's pretty clear from the previous lectures. So first thing we'll do is import matplotlib.pyplot as plt. Okay, and after that, what are the other things we might need? NumPy, so as np. These are the things that we might need. And the first thing that we'll do is we'll create a point. Let's suppose we have a point which has x coordinate of 10 and it has y coordinate of 15, let's say. Okay, this is the value of x and y. Now in order to create a figure, so how to create a figure? The simple thing is we'll use pyplot approach, plt.figure, or plt. Let's suppose if we just say how I want to give the size of the figure first, plt.figure, and then I'll give the size. So size should be, let's say, 6 by 6 or something like this. And after that, what I want to do is, maybe I'll assign it fixed size because I do not want any surprises. Okay, after that I want to create a horizontal line and a vertical line. That's I want to create a coordinate system. So if this is my plane, let's suppose consider whole of the screen or this figure as my 2D surface, and I want to define a coordinate system on that. So how to basically do that? So we should do plt dot, and then we have axis horizontal line, ax h line. Okay, this is horizontal line, and this will take a lot of argument. You can see this takes a y argument and then floor, and the thing is we'll start it from, let's suppose, 0, and we can give it a color. Okay, color is equal, let's suppose I want to give it a red. You can get of opacity also, let's suppose line width also, so that it is a bit better than what other these spine lines will look like. Line width, let's suppose, is 2, something like this. Okay, and then we'll also have a vertical line. So this is horizontal line, and now we will draw a vertical line. Okay, the same thing for the vertical line. And now if I see it, you can see it over here. You can see that redness over here, and it starts to 0 0. And then I'll plot these things. Let's plot plt dot plot, and I have x and y. And they should come as a point, so that what I'll do is I'll also give it a text. Let me just copy this code so that I don't type all the lines. You can see this, and let's make it red. I'll explain all the points over here. The first thing that is, these are the coordinate points, and these are my x-axis and y-axis. Okay, and then what we do is we write this plot dot xy, and then we give this red color and the circles. This is what I mean by this, red color and circles. And now what is this plt.txt? We want to add some text onto this. Okay, that is this point 3,4. I wanted to add text, so I said add this coordinate, add this text, because xy is the coordinate. I just want it a little above it, so I'm saying x plus 0.1, y plus 0.1. So I'm calling it a point and giving it x and y coordinate, and font size is 9. Then I'm limiting the x-axis to -5 to 5 and limiting y-axis from -5 to 5. That's why initially when I don't have these limits, so you could see if I just remove these things, so this origin will come around the corner. This was around the corner. So by putting these things, you are basically limiting it so that it looks quite symmetrical. And then we're saying we're just labeling normal label stuff. So here now you can see that this is origin. So this point over here is origin. This is my origin. Okay, I can also annotate this origin. Okay, and I can call it origin also. So this is my origin. Now you can clearly see that we were able to draw 2D Cartesian system. Okay, a similar thing can be done. We can now also create, let's suppose if we want to do it in 3D. Okay, how to do it in 3D? We must define 3 axes now. Let's suppose we'll do that. Okay, I have all these code over here. I'll just explain you the code. But when you are revising these things, do write each line by yourself. So here defining 3 points x, y and z, I'm defining 3 coordinates for the point, and now again calling this figure with this, and then I'm saying axis dot add subplot 1 1 1 basically means create this subplot, and projection is 3. This is important, this will create 3, and then I'm saying create a scatter plot with these coordinates x, y and z, and the color should be red, okay, and the size is 100, and then this is just labeling stuff. So if I just show this to you, so you can see this is x axis, y axis and z axis, and this is the point on 3D on a 2D surface. We have somehow projected this on 2D surface, we projected 3D points. Okay, now how to create vectors? We've also seen vectors in there. So now if you want to connect the lines, from the origin, so how to do that? So to do that, what we have, there is a method called as QUIVER. Okay, so I'll do that. Let's suppose we have 2 vectors now. So these are the vectors. So we have v1 vector and v2 vector. So this is from a computer science point of view now. So you saw that we have a point. Actually, this can be thought as a point. Each vector can be thought as one point. Or other way of looking at it is you can think it as a line going from origin. So this is 2, 3 is a position of vector 1 or point 1, and vector 2 is minus 1, 4. Now what we want to do is, if we want to plot them as vectors, plot them as these lines, which usually you will see physics people doing. Okay, so how they will do it? So let's first create the figure. Okay, this is the object oriented approach, and now the second thing is we'll use these lines. So this is how we plot these arrowed lines. So this is at starting from 0 0, this means start from origin, and take the first value, that is 2, and take the second value of v1, that is 3, and have this angle xy and scale it, and these are all the arguments that you can see in the document. This will basically just create an arrow, okay, starting from the origin. So I am doing it for v1 as well as for v2. Okay, now if I show you this, so this is how it looks. Now it goes out of this frame. So in order to do that, we'll set these limits, set x limit and set y limit, so that will bring it in the range. And after that, let's say we want to set the labels and other things. Not difficult, so they should be quite easy for you people, because we have been doing a lot of matplotlib now. So this is setting the limits, this is set label and title, show the legends, and add the grid, and this is horizontal line, vertical line, again the x-axis and y-axis, and show the plot. Okay, now you can see this is my vector v1 and this is my vector v2. So these are 2 representations which I usually use. Either I'll use a point or I'll use these sort of vector representations. If I have to rotate these things, I sometimes may just rotate the points, and for the visualization purpose, I sometimes may use these vectors. So whenever I am speaking about the vector, 2 things should pop into your head. The first thing, as a computer science student, you should have in the head that there are some array of numbers, is there. And the second thing that should be there, from the visualization point of view, it is either a point. If it's a 2, let's suppose if it's a vector which has only 2 numbers in it, let's suppose some x1 and x2, then it should be somehow drawn in a 2D Cartesian plane, and you can think it as a point. Or the second thing that you can think it of is like this. So this is a vector in some plane. So this is a vector. If we have 2D thing, this is a vector. And if it is 3D, accordingly we will have the 3D vectors which will be in the 3D plane. Is it clear? Are these visualizations clear? I think there is no new stuff which I am just showing the matplotlib of doing it. I hope that this is clear to everyone. Any questions on this? Let's create one more video, because I have also introduced you the basis vectors. So I won't say what basis vectors are right now, but basis vectors are the vectors by the help of which you can take a linear combination of these. You can combine these vectors to get any vector of the vector space. So what I have done over here is, so this is the normal import statements, then getting a figure, the normal stuff that we do, then drawing the x-axis and y-axis, okay, and this is defining 2 unit vectors. These are my 2 vectors, 1 0 and 0 1, as I did previously v1 and v2. Now I have defined it as I hat and j hat. So these are called as basis vectors of R2. So they are standard basis. Now again the same thing, I am using this method for this I hat and j hat, so as to just draw these arrows, and then I am having this text annotation on these things. So I am calling these text annotations, and again the same thing. Now I am drawing one more vector. Okay, this is one more vector that's having coordinates 2 minus 1, and drawing one more arrow by using this function. Drawing one more arrow, you can see it over here. Okay, and then I annotating that thing also, and setting the limits, setting x limit, y limit, and set aspect also, and then setting this x label, y label, and the legend, and then I'm showing title 2D coordinate system with basis vectors and a sample vector. So now if I draw this, you can see it. This is my y-axis, this is my x-axis. Okay, this is my I hat, and this is my j hat. I think j hat's annotation is a bit, we can fix it maybe. This is the j hat's annotation, okay, and we can fix it maybe plus 0.5 or something, plus 0.5 plus 0.5. Okay, now I just added something so that the vector shifted a bit, but this exactly is not now the j hat. I actually wanted to shift the text annotation. Text should be shifted, not the vector. Now I have just shifted this j so that this is not hidden behind this. So what I did here is, this is my basis. So this is j hat, this is I hat, or I cap or j cap. So these are the standard basis vectors of 2D coordinate system, and this is any vector. Okay, and this vector, if you see this, so if you see this vector, so this vector over here, if you see what is the value of this vector v, so v has the values 2 minus 1. Okay, 2 comma minus 1. Okay, and this I hat, this is 0 1, this is rather 1 0, and this is 0 1. So whenever I told you, whenever I speak out a vector, so vector should be thought like column vectors by default. So 1 0 and 0 1. So this is my I cap, this is j hat, and these are called as standard bases. Standard bases. Why are they called as bases? Because you can have any vector from this R2. So here this is called R2 because each of the values is a real number, and we have two coordinates for each of this. So these, if you take these base vector, you can just take a combination of these things and come up with any vector. So if I, let's suppose, want to come up with this 2 comma minus 1 vector, so what I can do is I can say 2i cap minus 1j cap. So I took a combination. So I took combination of this I cap and j cap, some linear, it's not non-linear combination, it's a linear combination. I just took 2, multiplied this vector with 2, and multiplied this by minus 1, so as to land up with this vector. So that's why these things are called as bases. So basis basically means if you have a set of vectors by the help of which, if you take a linear combination and you are able to get all the vectors that are there in that vector space. So consider this as a vector space. So this actually is a vector space which is technically called as R2 vector space. So why R2? Because each of the vectors is represented like this. So you have a real number over here, you have a real number over here, and you have vectors like this. This is R2 vector space. So these are the bases, these are standard bases. Okay, and there can be multiple bases also. This is my I hat, this is my j hat, and this is my I hat, and this vector is represented by the linear combination of these vectors. I hope that this is also clear. Now moving forward. And the second coordinate system that we saw is called as polar coordinate system. Okay, we won't use it much, but I just wanted to show you that we can also draw it using matplotlib, and I hope that you will be able to understand this code on your own. So here you can see that the same thing, we are using these vectors, but instead of these axes, we are just adding this, set theta 0 is equal to location this, and these are the additional things that we are doing. So this is how polar coordinate system will look like. So there we have a theta and the r. So if you remember it from the previous lectures, I have shown you that there are a couple of different coordinate systems. The two things that I explained was, the first is coordinate system, Cartesian coordinate system, and second was polar coordinate system, in which we have this r and theta, and we also saw the conversion between these two. If we have a point, it can be shown by r and theta in polar coordinate system, and the same point can be shown by some x1 and y1 in the Cartesian coordinate system. I think this is pretty basic code which you should be able to read by now, because you have done a lot of matplotlib. Now moving forward with the next topics. Then the second topic that we saw is a distance in 1D. So that means let me just hide this code window. So we saw distance of a point from origin. So I call this point, this is a vector, whatever you call it. Okay, what is the distance? So if you have a coordinate system like this, so if you have a point over here, and what's the distance the origin from the origin? Okay, so we have derived it by using the Pythagoras theorem. So if you have this, the distance d, so this is, let's suppose this is my coordinate system, this is my point P, and it is x1 comma y1. So I showed you that this d is equal to under root of x1 square plus y1 square. Okay, so this is the distance d, and we have extended it to nd also. So if this point is not just 2 dimensional, this is n dimensional. So what we can do there is summation of I is equal to 1 to n xi square under root of this. Okay, and this is the distance d. How to compute distance from the origin? Okay, let's suppose you have a point 1 comma 5 is a point 2D coordinate system. So what is the magnitude? It's also called the magnitude or the distance from the origin. So you can say 1 square plus 5 square under root, this is equal to that. Okay, this is 25, 26 and root of 26. Okay, now how to basically show you an example of that. Let's see it in 1D, and then maybe let's suppose we'll see it in the 2D. We'll see it from the by 2D I mean if we have 2 points and how to show the distance from there. Give me a second to bring this code window back. Okay, now how to code these things? If you have to code these things, again let's import this matplotlib that was already imported over here. So now we wanted to create points. Let's suppose we have 1D, 2D and 3D points, something like this. Okay, this is my point 1D. It needs just one value to represent it. Point 2D 3 and 4, and point 3D has 3 values. Now how to compute distance? Okay, distance in 1D can be calculated. How to calculate? Just take the absolute thing, absolute of 1D. If it is -5, so I can say distance is absolute of -5. I basically want give it the positive distance. And now how to compute the distance in 2D? This is how to compute distance. So point of, take this first and square it, take this second thing, square it, and then take a square root. Okay, so that's what I'm doing. This point of 2D of 0, that means this 3, square it. Okay, and then add, what should I add? Point of 2D of 1, that is this 4, square it again, and then apply this NP SQRT. Okay, this is basically doing the summation. This is doing summation of first squaring this 3 and then squaring this 4 and then taking under root of that. Okay, so how to compute distance of 3D? Pretty similar. Okay, and we just have to add one more thing over here. NP dot square root of this point 3D, take this point, square it, take this point, square it, take this point, square it, sum them all, and then apply the square root. Okay, this is how we have calculated distance. Now in order to plot them, this is just the plotting things that we have to do it now. So we'll create a figure like this, and this is a pretty big figure, so I'll cover 8,4. So we're creating 2 figures and then selecting if we have to show the distance of the point from the origin. So let's suppose I want to show it 1D point. So selecting this axis 0 and plotting this 0 and 1D point. The marker is this and color is this, marker size and everything, and I am also adding x-axis, y-axis, and limit, everything. If I show you, you can see this. The distance is 5. Okay, but in the next plot, let's suppose if I want to plot something in 2D. Okay, so how to do that? I just want to create. So here now select this axis 1, plot, and then have the 0 and point of 2D 0, and then 0 point 2D of 1, and everything is similar, but here we are using the scatter plot. Okay, this is point 2D. Why is this star used here? Because I want to unpack these arguments. Okay, this is a tuple. If you see these points, they are tuple. I can unpack them. So that's why this star is added over here. Okay, and then I want to show this x projection and y projection and setting the limits. If you see this, this is how it can be shown. Okay, and this is the origin. Okay, this is my origin, and this is the distance, total distance. From here, this is the origin, and to here. So here the distance is 5 square, because we have 3 square plus 4 square. So this is 5 square. So this is how we can show the distance. Again, if I want to show it in 3D, so pretty similar. So I'm defining origin point, I'm defining the point, I'm calculating the distance. So this is also, this norm basically does the same thing which we did over here. I just wanted to show you one more thing about NumPy. So this is np dot square root, and we did all of these things by our own. If you just define this np dot norm, so it will do the same thing. Okay, point minus origin and calculate this norm, and then we can print the distance. We can create this figure, add subplots, add all of these. So if I show you this, so this is how it will look like. This is my origin, and this is my point, and then this is the distance between it, and distance is 3.74 something, because I have printed the distance in the middle. Okay, no, how to calculate? If I just want to calculate distances, so I can write a function about it. So let's suppose I'll write it like this. So definition, calculate distance. So calculate distances. So it's not every time that we want to just continuously do this norm. So what we can do is we can write a function to calculate distances. So we'll just give it a point as an argument. So point will be 2D, ND, 3D, whatever it is. So it will take that point as an argument, and it will apply that squaring of each element, and then applying the square root at the end. So what we can do is we can first calculate dimensions. So dimensions will be length of the point. What is the length of that point? Okay, now after having the length of that point, so now we should be able to compute the distance. How to compute the distance? So we'll say distance is equal, so now we'll apply this np.sqrt, np.square root. Okay, then what should we apply square root on? We should basically have the sum, np.sum. So we should apply sum over all the elements, and let's say we have this. We also will do np.square, square, np.square of points. Okay, and then this is the distance. This is point, and let's return the distance. Okay, we can return this distance if we want, and the dimensions also. So let me show how it works. So let's suppose if I have defined a point, if I defined a point like this, if I define, let's suppose point 2D, something like this. So I'll call np.point2 np.array. Let's show a point 2, 3 or 2, 5. So I want to find its distance from the origin. I'll just call this function now, calculate distance, and give this point as an argument. Point 2. Okay, you can see this. This is 5, 3. This is that one. Because I didn't want to have this function where I'll just write the code again and again. So it's better to have it written as a function. So what it does is, so it will first perform this np square on the point, because as you know that, so if I just apply this np square on this, so I want to show it separately first so that you know the what is going underneath the hood. So let's suppose we have this. So this point can be, let's suppose 2, 5 or 2, 3. You can see that it squared each of the elements, because you know that NumPy supports broadcasting and vectorization. So here it did the square of this and square of this. Okay, that's what this np squared does. And then I can do np.sum. Okay, and I can do np.sum. What it does, it will do is it will initially take these square things and then sum them together. And you can also mention the axis, but by default axis is 0. So that's why it is summing them over there. There you can still see the number, and then you can apply the square root. That's what is happening over here. So I have points now. I can have points in ND. Let's suppose this is my point in ND, and I just want to add some more things. And now you cannot visualize this, but mathematics can give you the tools to compute it. You just need to compute. So this is the formulation for the ND. Okay, and how can I write it? So this is summation. If you want to write in LaTeX also, so I can also write in LaTeX, but it's all right. You can understand this. So calculate the distance of these point ND. So it will initially square all these things together, and then sum them up, then apply the square root and show the distance. Okay, and now let's suppose if we have to show a couple of examples. I have written those here. Now you can see it. So we have a point 1D, we have a point 2D, we have point 3D, and we are calculating distance. Same thing as I showed you, and then I'm just adding some results over here. Okay, this is distance of the distance of a point or a vector. A point can be thought of a vector or a point, howsoever you like it, and then this is the distance from the origin. So it was just the demonstration of how to write in the code. And now we saw the distance between 2 points also. So let's suppose if you have 2 points in 1D, 2D or 3D or ND, so what is the distance? So I'll just remind you the formulation there, and I know you people can derive it. You have revised the lectures. So what was the formulation for that? So if you have, let's suppose, Cartesian plane like this, I'll just speak about 2D. So if this is the point and this is the point, and you want to see the distance between the points, okay, so what was the formulation? The formulation was x2 minus x1 plus y2 minus y1, and you have to keep on squaring them and then apply the square root. Okay, this is what you should do, and you will get the distance. You'll get this d dash. Let's suppose this is d dash, and then you can plot it also. Now let's suppose we do it in 1D, 2D and 3D. Okay, if you know this formulation, and we have derived in previous lectures, this was just for the sake of just refreshing. Again, what I'll do is I'll import these libraries. Okay, now I'll create, I'll again write a calculate distance. Now this distance basically is between the points. So it will take 2 points as an argument. It will take 2 points. So it will take point 1 and point 2. Point 1 comma point 2. So it will do pairwise subtraction first. Do the pairwise subtraction and then square them up. And after that, what you should do is you should apply the under root. You should apply the square root. So the first thing that we'll do is we can also return dimensions if you want. So that's what I'm having this dimension for. And now we should do this. Oh, oops. Sorry. If you see this, I have imported these libraries, and then to calculate distance, I'm saying give me 0.1 and give me 0.2, and the formulation has been seen in the earlier lectures. So now I am calculating the length, the dimensions. So now what I can do is, okay, distance is equal to np linear algebra dot norm. So this will take np array and subtract it, and you can again do it the same thing. You can again apply the square, then the sum, then the under root. So that operation is called norm. Okay, to apply sum and apply under root. That's to first square the things up and then sum everything and then apply under root. That thing is called as norm. Okay, over here if you see this, so this basically is operation like this. So you first apply square of individual quantities, and then you sum all these squares, you apply sum. Okay, and after the sum you apply square root when you do this sqrt. So this operation is called norm over here. So that's why it's called np linear algebra dot norm. Okay, so it is basically doing this, applying square for individual elements and then summing them up along the axis 0, then applying the square root on that particular value. Now we can just return this distance and dimensions. So returning it over here. So now if you want to plot it, so what you can do is, I can show you 3 types of points, point 1D and point 2D, point 3D. So let's suppose we have this is my points in 1D, 2 points within 1D, and calculate distances, and this is calculate distances for these points and calculate distance for these points. Now if I want to just display the results, you can see this. So 1D distance, 1D space, distance between points is 5.0 in one dimension, and now for these distance is also 5.0. Let's now change the value so that to see this code is working right. Yes, it is. So now distance in 3D is this because it's using the formulation. Okay, why am I showing you this? Because I want you people to get comfortable in code. Whenever we are reading an algorithm, so we should be able to convert into the code. The first step is that you understand the theory of it. If you understand theory, nice, so you can write it pen and paper. Now the computer should give you additional capabilities. You should translate whatever you know, whatever you can do on the paper on the code. So that's what I'm trying to do. So you know how to compute the distance from the origin. So you know how to compute the distance between 2 points. Now basically how should you translate that thing in the code? That's what I'm trying to do. And at the same time, you want to visualize them. Okay, what will happen? And if it's in the brain, how to take it out and show it on the screen. That's what we're doing right now. So we have this points P1 and point P2. So here we calculate dimensions first, then computing the norm of that, and then return the distance. And now if you want to visualize them, okay, let's suppose I want to visualize. That's why we have done extensive, the matplotlib has been covered extensively so that you don't have a problem understanding this code. Otherwise, if I have to write all the code by myself right here, so each of the code will take at least a couple of minutes and we won't be able to cover anything. So that's why I have just written the code on the other desktop. So here this figure axis, and I'm having these plots. I want to create 1 by 2, that is I want to have 1 row and 2 columns, and this is my figure size. Now selecting the first axis in that figure, and I'm adding the horizontal line and the vertical line. Now I am first joining these points. So I'm showing this is vector, let's suppose point 1, and this is point A and point B. These are 2 vectors for that. Now I am adding a scatter plot. By scatter I mean I just highlight these 2 points, and then I am adding a plot, and these 2 points are basically connected by these dashed lines. Okay, and similar thing is done for 3D. If I show you this over here, so you can see this is the origin, and this was my point A, and this was my point B. Okay, and these blue things are my original vectors, and this green is the distance. And over here, this blue thing, they are the original vectors in 3D, and this blue, maybe a light blue, it looks like light blue, and this is the distance. This is how you should imagine these things. When am I saying distance between 2 points, and this thing should somehow get into your head and it should pop up there. So now we have computed the distances also. Okay, I think this should be very easy to, this code should be very easy for you to understand because we have done a lot of practice of this matplotlib. Okay, so what's the formula? I have actually created a lot of these things, but I don't want to show everything. It will take a lot of time. So this was our the first thing that we saw in the distance from the origin, or it's also called the magnitude. Okay, because magnitude is from the origin. And the second point we saw is distance between 2 points. If you have 2 points, okay, and then how to basically show the distance. And why am I covering this? Okay, so what is the point behind this? So let me just clarify that so that you don't get bored. I know this might feel very easy right now, but once the layers of abstraction keep on adding, then it feels very difficult. So why am I computing distance? Because I said distance is somehow measure of similarity. Okay, and everything in computer science is a number, and everything that you, every data thing is a number. So let's suppose you have two words. Okay, you have a word, let's suppose smile, and you have a word, let's suppose laugh. Oops. Okay, let's suppose these are two words. Now you know that these words will be converted into a vector. So they'll be converted into some vector representation, and this thing will be also converted into some vector representation. Okay, and these vector representation will lie in some higher dimension. Let's say these are lying in 2D. So there is a number 1 2 which represents smile, and there is a number 2 8 which represents laugh. Okay, now we can compute distances, because we know that this smile and laugh, they are somewhat similar in the meaning. So distance between them should be quite less. So if distance is less, that means these things are quite similar. So let's suppose now we have anger. Anger is almost opposite of smile and laugh. So distance between smile and anger should be way more than the distance between smile and laugh. Okay, that's why we will use them. That's why I'm showing you the distance and distance from the origin and about these vectors, because everything that we'll see is a vector. So in here, if you know the recent paper, I have also discussed it in one of the algebra classes, that was called as word to vector. That's what the algorithm they have used. So they are taking the words and they are getting a vector out of it. So but the thing that they wanted is, so similar words should get somehow similar embeddings. So by that they mean, so if they are very similar in meaning, so they should be very close to each other. If they are opposite in meaning, they should be quite far from each other. So that's why we have to learn the distance. So distance is somewhat showing as the similarity. Okay, that's why we should know these formulas. So when you compute the distance between 2 points, you basically are in a way computing similarity. Is there clear? Any questions on this? So again, to remind you, the motto of this session is two things. The first thing is, if you know something that you have understood and you can do it by pen and paper, how to convert that into code. That's one of the aspects of this lecture. And the second thing that I wanted to is how to visualize that thing. Okay, if you have a computer in hand and you know the things that are going on and you want to visualize them and you want to plot it somehow. And these are two things that I want you to take away from this lecture. The first thing is, whatever you can do by hand, you should be able to convert it into code. And the second thing is, you should be able to visualize it. If you can do these two things, you can read any book after that, and just if you understand it and if you can do these mathematical problems, you should be able to write the code also. And after that, we have seen unit vectors. So now we are done with distances. So we saw a unit vector. So unit vector basically is a vector which has unit magnitude. So by unit magnitude, I mean, you know by now that magnitude is, we have defined magnitude like this. If we have d, so magnitude is of d is something like this, under root of summation of I is equal to 1 to n xi square, something like this. Okay, so if you want to compute the magnitude, if this magnitude is unity, that vector is called a unit vector. So this unit vector, it is usually used in the direction. So if you want to give it a certain direction. Okay, let me just write the code to show you that. But when you are revising the lecture, please pause and just try to write these lines by yourself. Do not just copy paste. So here I have vector in 2D. Okay, and the magnitude is again the same thing. Square this up, apply the square root, and this is basically computing the norm. I could have directly used np.linearalgebra.norm, but here this is the expand operation. How to compute unit vector now? This is the vector, and each component should be divided by its magnitude. So as when we square the things, when we now compute the magnitude back, it should be unity. So that's why I'm dividing it over here. Okay, and then the same thing is, have this arrow, and the second arrow is for the unit vector, and then set these limits. Okay, so you can see this was the original vector, was this blue vector, so with the magnitude 5.0. Now we have this unit vector. You can see this, it has the magnitude of 1. Okay, this was the unit vector. Then the most important thing was dot product. Okay, coming to the dot product, and many people had some hard time understanding that time what was the dot product. So in maths, the simple dot product, if we have a vector and if you have vector b, so we say a dot b is magnitude of a, magnitude of b, cos of theta. Okay, this is one of the definitions. We have a vector a, let's suppose this is a vector, and this is vector b, and they have a vector theta. So just find the magnitude, and multiply them together and see and multiply with the cos theta. So this is dot product. Okay, we say we can multiply two vectors in a different way. So we have cross product and dot product, but the most important that we'll see is the dot product. Basically, dot product is a special case of what's called as inner product. inner product. We'll see what the inner product is once we go ahead in linear algebra classes, but here this dot product is a special case of inner product, and an inner product has some specialities and why is it used. So if you have any vector, you can just compute the dot product like this. If you let's suppose have vector 2i cap plus 3j cap, this is one vector, okay, and then we have 3i cap plus 6j cap, something like this. This is my vector A and this is my vector B. How to perform dot product? Basically take all of these, take this 2 and 3, 2 and 3, and then you have this 3 and 6, something like this. You can element wise multiply them. So you can say 2 multiplied by 3 is 6 plus 18, and this is equal to 24. Okay, this is one of the way to compute if you have the components. Okay, otherwise you can just find the angle between these things also by doing this. You can find the magnitude of A, magnitude of B, and what's the angle, and how to find the angle also. You know how to find the angle from this. Okay, you can use this equation. And now what this dot product was there for? Again, this is a measure of similarity. So dot product is the operation itself. This operation is made up of multiplication and additions. So this operation was there for the computer science. We usually use it for similarity. We want to find similarity. As you can see, distance was there for similarity, and dot product is and the way of finding similarity. So while this similarity it's used everywhere. Okay, let's suppose you want to find, as in the example that I showed previously, you want to see how similar two words are there, so we can use the dot product. Or maybe let's suppose you have two data points and you want to see, okay, is there some variability? Can I remove one data point? So what should the model trained on? So let me explain that example. Let's suppose you have a model and now you have the data. So in the data you have a lot of points which are quite similar, but your model, you want to give model such a data so that model learns quite well. So you do what's called as active sampling. So active sampling basically means you take the samples which have more variance, which have more variety. So how to basically capture that variety, how to mathematically have a matrix where we capture that variety. So we can use this similarity. So how to do that? We can maybe use dot product, a measure of similarity. So this dot product has a lot of things to do. I think we have already seen it in the previous lectures. It is also used in attention and things like that. Let me code it first and then I can show you some applications. I have one application with me that I wrote the code today. So how to now have the dot product first, and we'll compute dot product, and we'll also we'll also plot that. Okay, now, and NumPy makes it really easy because in NumPy there is a function np dot. Okay, if you have vector v1 v2, there is a function np dot. Okay, this is the function. So if you have points v1 and v2, so this is the, if I have this point v1, this is equal to, let's suppose, np. Sorry. So if we have this vector v1, so v1 is np dot array, and let's suppose it has 1, 2, 3, and now let's suppose we have another vector v2, and it is 4, 3, some, let's suppose 8. np dot, if I just want to print it, you can see this is the dot product. So basically what it does, 1 4 is 4, 2 2 is 4, 4 4 8, 8 plus 24 is 32. That's the dot product of these things. Okay, otherwise you can do it by your own. You can just run a for loop, but you know that the thing over here is that this NumPy is optimized because it uses vectorization and it uses broadcasting to make the operation similar. Now we want to plot it, so I'll write a function over here, but I have given a lot of things. I should not do it, and let me do it. I'll explain this. So here you have the first thing that you saw is we'll write imports, standard imports, then a random seed for reproducibility, and then I'm saying plot the vectors and show the dot product. So what I'm doing is I'm getting the axis, okay, whatever axis I want it plotted on, I'm getting vector v1 and vector v2, and I'm getting angle in degrees if you are giving me the angle. So np dot is like this, okay, and this is the dot product, and this is the norm. So v1 magnitude, v2 magnitude. So this is if I have to compute ab cos theta. So this is the angle, how I can compute the angle. Dot product divided by v1 magnitude, v2 magnitude. So this is calculate the cosine angle. Okay, now I'm having these arrows to vector v1 and to vector v2. Okay, and then I'm computing this arc also and adding this patch. So this adding patch basically adds those arcs. You can add rectangles, you can add anything that you want by using this add patch. So then now I am setting the limit for x and y axis, showing the grid, and then having the horizontal line and the vertical line, and then adding some text also, setting the title for it, and now I am creating this figure, axis 1, axis 2, axis 3 and axis 4. So over here this is my vector 1 which is fixed. So these are the angles. I want to basically compute dot product at different angles, 0, 45, 90 and 180. So I am saying for ax and angles, zip all these things together, okay, ax1, ax2, because I want to create 4 figures, and then give the angle in radians. So I have an angle, convert into radians. So degree to radian is a function in NumPy. So I am saying now this is my v2, which is this. So np of cos of angle, comma np dot sine of angle, and plot this vector. Give ax, give vector v1, give vector v2, and the angle. So if I show you like this, you can see the 4 figures. The first thing is at 0, okay, and second thing is at angle 45. You can see angle is 0, cos is theta is 1, as 0.71 and something like this. Okay, all of these things you can maybe draw it on the paper, but here the point is how you can make it. Again, have a look at this function. So this is taking the axis where you want to plot it, and this is taking v1 vector first and vector second, and the angle in degrees between these two vectors, and it will plot them, okay, and it does these calculations which I have explained. Questions? I want to just ensure that it looks easy to you, because you have seen matplotlib. So can you raise your hands that at least it will give me some assurance it is easy for you people, so that I won't just gloss through it. Beautiful. This is what I expected from you, that it should look easy after a while. Okay, now let's do an example on dot product. This is what I wanted to do actually. I wanted to show you the similarity. Okay, maybe this will be an example where we'll engage maybe a bit. It will be sort of time taking also, but I want to make a point through this. Okay, let's suppose what we have some movies, okay, and in the movies we have been given description of a movie, and we have been given genre of the movie, and we want to see how similar they are. Let's suppose if I watch a particular description is given to me, okay, I want to make an algorithm such that if let's suppose I like the description of one movie, maybe if some other movie which is close in description for that, so I just want to maybe watch that movie also. I just want to make a movie recommendation system, and this will be just purely based on the dot product. Okay, I'll import some libraries. So what I'm doing is I'm importing NumPy, matplotlib. So this sklearn basically is to convert the text embedding, whatever we have text, I want to convert that into embedding. So that's what I'm using this sklearn for. And then this seaborn is just a wrapper around the matplotlib. Okay, let's suppose I have these movies. This is my sample movies with the description and the genre. Oops. So these are the movies. The movie name is Dark Knight and description is this, and the genre here, if you see it, this is called as one hot encoding. Okay, let me explain this. I think this is pretty clear, but I should explain this. Why this? Let's suppose I have a vector which represents genre. So I can have genre action, crime, thriller, comedy and romance. So these are my genres possible. So it can be more genres than this. I'm just keeping those things. So if the movie belongs to particular genre, so I'll put a 1 there. If it does not belong to that, I'll put a 0 there. So for example, if this movie contains action and it contains crime and it is thriller movie also, so I'll keep 111 there. This is not comedy movie and this does not contain any sort of romance. So here you can see this 11100. So this is one hot encoding. Okay, or maybe categorical encoding. It sometimes called one hot. Sometimes it's just you keep one at one place, and for others you keep 0. So this I can call it categorical encoding. Categorical encoding. Because I have to convert the things into numbers. So genre I have to convert into numbers because I cannot write just action or crime and thriller. So I just kept 111 and 00. And for other things, if you see description is crime, thriller, police detective chases bank robber in the Los Angeles. This is heat. This movie is and the movie. So genre is crime and thriller. So again the movie is, the name is Hangover. Description is this and the genre is this. The first thing is you have to somehow convert into embeddings. For the genre we have done categorical embedding. We have just put the one over the places where it belonged to them, and for the others we have kept 0. Now the thing is we have to convert the descriptions. Okay, we have to vectorize it. So how to vectorize it? I'll just write the code. You don't have to reason about it because we'll go to sklearn and we'll learn it how it does internally. So it calls this count vectorizer and removes these stop words, and then gives takes these movie descriptions, okay, and convert them into vectors. Okay, so if I just print these description vectors, so you can see this for each movie they have some description. Okay, some vectors are there. Okay, some binary representation. So these are my descriptions. Okay, just think it that I have just taken the descriptions and I have converted them into some vectors, some numbers. Okay, so genre vectors also. So I'll also convert them into vectors. Okay, now if I want to print this, I am vectorizing them. You can again see genre. I am just taking basically these vectors. I am taking these vectors and making embedding, because computer only understands numbers. It does not understand anything except numbers. So I have somehow vectorized these descriptions. I have somehow vectorized these genres also. Now I have both the things. I have description with me. I have genre vector with me. Now what I want to do is I want to compute the similarity. I want to compute similarity based on the description and based on the genre. So what to do? I can use the dot product. Okay, I can maybe write a function which is called definition calculate similarities. Okay, def calculate similarities and give me these vectors. So what I can do is I can normalize it first. By normalize, I want to get into a certain range so that it is. So by normalization, I mean it should not depend on the length. Okay, and then calculate the dot product. I am taking this normalized vector and normalized vector transpose. Okay, basically computing the dot product of these things within itself. Okay, and this is giving me the similarity. Now what I can do is, if I want to see similarity between genre and the description, so how I can do it? I have description vectors for all the movies in this. I have genre vectors in this. So now how to do that? So I'll say description similarity, calculate similarity of description vectors. Okay, it will take all the vectors and give me the description similarity, and this is the genre similarity. So what it is basically doing over here, if you see it, so let's suppose if it is taking, I'll now generalize it. Again, being a mathematician, I'll do M1, M2, M3, M4. Okay, this is M1. I should write it a little better. It deserves to be written a little better. M1, M2 and M3. Let's suppose we have only 3 movies. This is M1, M2 and M3. Now each of the movie description is represented by numbers. Okay, this is number, this is all of these are numbers. So now in order to find similarity, so what I am doing is I am performing the dot product. So I am performing M1, M1, this is the dot product. I am getting some values over here. Okay, and this is showing the similarity. And after computing the similarity, I am computing 2 types of similarity. One is called description similarity and one is called a genre similarity. So description is converted into a number and I am performing dot product, and then this genre is taken as a vector, and we are computing the similarity. And now we can compute the heat map. We have seen image show, heat maps, all of these things we have shown, and so as to see the similarity. So how to do that? It should be pretty easy. The plotting should be pretty easy. So SNS, to call it heat map, give the argument as this the similarities, and the similar thing for this heat map for the similar, and we'll have 2 sort of heat maps and we'll see how much similar are they. Is there something wrong? So I just want to show this. Why is it not showing this? Give me a sec. So as to fix this code, that's why the problem is in the code. I wanted to copy everything and see. Yes, you can see it over here now. Maybe there is some mistake in the code. I'll again go back, so I'll just delete these things. Yes, so again the same thing. If you see from the this is the import, normal import. This is my sample movies, converting them into vectorized forms first, convert the description into vectors, convert the genre into vectors, calculate the similarities by using the dot product. Okay, compute the similarity between the descriptions, compute the similarity between the genres, and then just plot this. So I haven't actually added this. I did not added the axis, the axis 1 and axis 2, and then I'm saying sns.heatmap, give this so you can see the heat map. So if you see the diagonal 1 1 1, because each movie is similar to itself, 100% similar to itself, that's why it's giving the 1 score. Okay, when the dot product is 1, that means it's perfectly similar. Okay, so if it is 0, that means it's totally dissimilar. And if you want to see the similarity, so heat has some similarity with let's suppose some other movie is there, heat and the Dark Knight. Okay, this matrix will be symmetric. Why symmetric? Because we are having movies where if you see this movie based on genre, so you can see heat is quite similar with the Dark Knight in terms of genre also, and heat is quite similar to the Die Hard in terms of genre. It is almost matching a lot. This is a simple, very simple movie recommendation system. Okay, just based on the dot product. If you see this, we are just taking these vectors. Okay, normalize all these things together and then find the similarity. Okay, basically I'm taking, so what is this operation doing? I'll tell you what this is doing. Maybe it might be a little confusing for you because you are not well versed with matrix, I assume, at this point. Maybe some maybe and some might not be. Let's suppose here we are giving a vector, so we have a bunch of vectors. So this is the data matrix. This will be whole matrix. This is our, let's suppose, description 1. Let me write it better. This is description 1, description 2, description 3. Okay, this is the matrix that is there of descriptions. So I am just transposing it. So this is my D1 transpose now. This is my D1 transpose over here. So I'll write it like this. This is D1 now, this is D2, and this is D3. That's what this transpose is here for. So if you see, I'm getting the whole matrix, calling it as vectors and normalizing it. So how to normalize it? Take all the vectors, and then this is just to get in the certain range. So if you see this dot product, I'm saying normalized vectors, comma normalized dot transpose. So this is taking this whole matrix, and this is transposing the matrix and performing the dot product accordingly. So this is this is taking D1 transpose, then computing D2 transpose. Okay, that's what it is doing over here in this dot product, and that's why it's giving these similarities. It will give a list of these similarities. Okay, so basically what it will do is it will give me a matrix like this. Okay, which I already did, M1, M2, M3, similarly, and this all of these things will be dot products. That's what it is doing over here, this line. Okay, and this line is normalizing. Okay, by normalizing I mean I just want to get the values in the certain range so that they do not blow up. The simple representation how you can make by just using dot product, how I just made a recommending system. It's very bad recommending system because the embeddings are not right, and we are using quite only dot product, which we could have used more of the things, but I just wanted to show you how dot product can be used to make the things like a recommending system. Any questions on this? So now I showed you the power of this dot product in calculating the similarities, and we just made a small, maybe a very terrible recommending system for movies. Based on the genre and the descriptions, and even vectorization was not good that I can see. Now coming to the next topic of projections. So what are projections? So if you have doubts about what projection is, we have covered that in the previous lecture. Just to again refresh it a bit. So if you have vector B, let's suppose, and you have vector A, okay, and you want to find projection of a vector A onto B, okay, and this will be the projection. It is like having a torch, and then this is the projection of vector. This is the projection of that vector. Okay, why is this projection used? So I have told there is an enormous number of examples. Like there is one example called as PCA, principal component analysis, which is used for dimensional reduction. Okay, and to just refresh, you should go to the previous lectures to see the different applications. And here we can directly see the formulation of the projection. Okay, so the first thing is let us see the projection. Let's see how projection looks like in the code. So if you see this over here, so I am applying this plot and project vector. So the first thing I am doing is importing the normal standard libraries matplotlib and numpy. So now calculating the norm of B, okay, and then calculating the projection. So you know how the projection is equal to, if I have to compute projection, the formula for the projection is, so if you have a vector A and B and you want to see the projection of A onto B, so projection basically is equal to, you take dot product of these A and B vectors, take dot of this, that's what this dot is for, and divided by norm of B, take the magnitude and square it and multiply this thing with B, and this is what projection, this is the formula of projection. Oops, this is projection of A onto B. So basically if you have a vector B like this and you have vector A like this, so the value of this vector, so which is projection, so this is projection of A onto B, so the value is equal to this. So perform the dot product and take the magnitude square and of B divided by that and multiply by B. So this basically was, I think it was actually A dot B divided by magnitude of B multiplied by B magnitude of B, and this was the direction. So this was the direction and this was the magnitude. If you have revised the lectures, you will be understand what I am talking about. Okay, so this is the formulation. Maybe I'll just cover it for you people. So if we have vector B like this, you have vector A like this, and you want to project it, so projection will be this vector over here. Okay, but what you can do is you can say A dot B is equal AB cos theta. Okay, and now if you can see this if this is D, so let's call this projection D. So this D, if you can see this, so this lambda times D is equal to B. Somehow if you just multiply this D with some lambda, you will get this B vector. Okay, and now you can, if you just put these values, you will get the magnitude. Okay, the magnitude of this D will be, magnitude of D you will get as A dot B divided by magnitude of B. How to get this? Because you know this D will be A cos theta, so this D will be equal to A cos theta. So a cos theta can be replaced by this d. So a dot b is equal to, so this is a cos theta, it can be replaced by this d, and this is b, and magnitude of b, and I can say d is equal to a dot b divided by magnitude of b. We're just taking it over. Now this is the magnitude of d, but what is the direction? Direction is in the direction of b, in the direction of where this b is. So, but b is not a unit vector, we want to make it unit vector. So we can say b divided by magnitude of b. So this is unit vector. So just multiply this b divided by unit vector. Okay, that's why this a dot b divided by b square and multiply by b. That's what the projection is. That's why the formulation is used here. So if you see this, so I'm computing the b norm first, basically magnitude of b. That's what this is. Okay, and then I'm saying np a dot b, computing the dot product and computing the norm, squaring it and multiply the b. This is the projection. Okay, now if I want to plot it, pretty easy, standard stuff. So this is figure and axis, plot these things, set the aspect ratio, give the grid, and origin should be 0 0, and plot these arrows. Okay, plot these arrows a and this, and then set it like this. These are the limits. Okay, and this is my x label, y label, and projection magnitude is this. And if you just have these values a and b, if I want to show projection of a onto b, so this is that. This is projection of a onto b. Okay, here I can say vector a is this, vector b is this, projection magnitude is 4.42, and this is how it will look like. Okay, I have created a little bit bigger figure, but I hope that you can just go through the code and write it line by line and ask questions to yourself what this line is doing, and it should be pretty clear to you, because you know enough matplotlib to understand this. Okay, this is the projection. So I told you applications are enormous. We'll use a lot in principal component analysis, where we'll do dimension reduction, and we'll use it in eigenvalues, eigenvectors, and things like that. Okay, and now we have to move on to the next part of where we discuss the decision boundaries. Is it clear so far? So while watching this series of lectures, the first 3 lectures were just introduction, and this is some sort of practical visualization of the 3 lectures. So what you should do while revising is, when you are reading the first 3 lectures, have this 4th lecture open on the separate window. So whenever the concept comes, and you should try to code it from this lecture. Okay, and it should be pretty clear to you after you code it, and maybe you can code it multiple times so as to get the better intuition and better understanding of these things. Again, to reiterate, 2 motives of this lecture. The first motive, if you know something theoretically, if you can do it on the paper, how to translate that thing into the code so that you can talk to a computer. Second thing, how to visualize to develop the intuition. Okay, now we're into the important part, which we'll be using many times in the machine learning and deep learning, is about the decision boundary. So what is the decision boundary? So decision boundary is a boundary or a surface which somehow divides your feature space, or your vector space, I'll call vector space in terms of mathematics, but we have this feature space because our features lie in that vector space. If it is R2, it is our 2-dimensional coordinate system, or we can call it, we have 2 features, this is our 2D feature space. So it divides that into 2 half spaces. Okay, usually these decision boundaries, if they are lying in that, so the basic example is of the line. Okay, and you should also revise the lecture on decision boundaries. Let me just hide this code window to show you that. Okay, the equation of line that we wrote is, so we said w0 plus w1 x1 plus w2 x2 is equal to 0. Okay, this is the equation of line which we have seen, and we said if, let's suppose, if we make an affine transformation, we can just remove this w0, we can write w1 x1 plus w2 x2 is equal to 0. So we can say this w and x, w transpose x is equal to 0. So this divide w is equal w1 and w2, and this x is equal to x1 and x2. Okay, this is the succinct representation of a line. So this is line in 2D, and a surface in 3D, and in ND we have hypersurfaces. Okay, how to now see this? Okay, let's bring the code window back. Okay, I'll do it in the both ways. Okay, so what I'll do is I'll just copy one snippet of code and paste it over and explain it. So now if you see it over here, the standard imports, import numpy and import matplotlib. Now I have to plot a 2D line. So this will be with 2 parameters. So I have w0, w1, w2. So this w0, if I have to make affine, I can set it as 0, and I'll say w1 and w2, and then I am giving the range of x1, the range of these values, x1, x2, the range of these values. So now in order to just plot the figure, I'm just making the plots. Okay, everything is written in the function. Now x1 is, so give the range of x1 from x1 0 to x1 1 and make such 100 points. Okay, and now how to compute x2 from the equation. So we have seen the equation, so you can see the equation was, oops, this is basically rearranging. The equation was this: w0 plus w1 x1 plus w2 x2 is equal to 0. So rearranging this, we can get x2 from it. Okay, so we have now w0, w1, w2, and we have x1 and x2 also. Now in order to plot this, pretty easy. Plot this x1 and x2, and now I am also separating a midpoint so as to show some w vector. So this is my normal now. So normal is, this w vector is my normal vector, which I call normal. I am just normalizing it and just adding these arrows. Okay, adding the grid and the style. Okay, so if I show this is the equation, then I am showing the text annotation. This is my equation, this is my slope, this is my intercept, and then I am adding it as text. Okay, and then I am setting margin as 2, set x limit, set y limit, return this figure and axis. So let's suppose the normal vector is this: w0, w1, and w2. So this is 3, 2, and 4. So I want to plot them. If I want to plot it, you can see the plot over here. This is that thing. If I change these values, let's suppose I change this value to 5. You can see this line is also changing. Okay, so in order to give me anything, you just have to give me this normal vector, w vector. So and I have also created here, this is the negative region and the positive region, and you know why they call negative and positive regions. So they are called as hub spaces. So on the point, the value is 0. So if the points which lie on this line, they'll satisfy this line and they'll give 0, and the points which lie on the green side, they'll be positive values because the value will be greater than this. Okay, and on the left, on the below region, that is negative region, the value will be less than 0 over there. Okay, on the line it will be 0. So we have seen that the positive hub space, negative hub space, the only thing that we have to change is w vector. So if you give me these w0, w1, and w2, I can uniquely identify a line. Okay, and this is like y is equal to mx plus c, where you give me slope and you give me, let's suppose, the intercept, I'll uniquely identify that line. So I am just rearranging that thing, so giving this w0, w1, w2. Okay, so if you give me this, I can uniquely identify a line. If I give you, let's suppose, 10, this is something like this, and it will also compute the slope. Do look at this code when you are coding it. And the second way of doing it is, you can, let's suppose, take this w as a vector. You don't need to take them as different numbers. Usually we'll take them as number. We will take them directly as a vector. So let's suppose how I want to do it is like this. So here what I have is the similar thing. So plot decision board. Now I'm getting w and I'm getting the x range from -10 to 10. This is the range of the values. So now if you see this, the standard step, just get the figure and axis and generate x1 points in between this range, x in between -10 to 10. Now if you see this, how to calculate this, x2 points from w transpose x. The equation basically is w transpose x is equal to 0, which I wrote earlier. This w transpose x is equal to 0. Now I have to get x1 and x2 from that. So this is the calculation that I have written here in comments. So this is w0, w1, and w2, and I can write, instead of w0, I can write 1, x1, and x2 transpose. This is equal to 0. Now the values I should get is for x2. So if I rearrange this equation, okay, rearrange this equation, so I'll get w0 plus w1, wx1, and wx2 is 0. So this is x2. This is what I will get. Now I know this w will be given to me as a whole vector. It won't be given to me as w1 and w2. And this is the second scenario. The first scenario was I was given these normal components of this normal vector individually. Now if I am given this normal vector as a whole, so I have to compute this. x2 is equal to minus of w of 0. Take the first element, take the 0th element, take the first element, and multiply to x1 and divide it by the third element. So this is how I'll compute the x2. Okay, and then the same plots which we have done earlier, just have the midpoint so as to draw the normal at the midpoint, and then add these arrows. Okay, add these labels, add these annotations. This is the annotation, set the margin. Okay, if I now do this, so this is a couple of examples shown here. So if you can see, I have drawn 3 examples over here. If I just want to show, let's suppose, example till example 1 only, I can just comment out this. You can see it over here, the same thing. But now if you see, this w is being given as a whole vector. This is not being just given as w0, w1, and w2, but actually it is given as a normal vector. So the only thing that you have to change in the code is this. You have to do it like this. Initially what we are doing is, initially we are getting w0, w1, and w2 separately. So we are getting it w0, w1, and w2, and that is what we are doing the calculations accordingly. But now we are getting as a vector. That will be the usual case usually. So the vector will be given as a whole to you. Okay, you have to make these lines. Okay, and these lines are decision boundaries. So they divide the whole feature space into 2 hub spaces, one negative hub space, one positive hub space, and they'll be used for classification. If I have a classification example, I'll show that. Give me a second or so. I think I have those examples somewhere written, but I just need to see it. If I just add one more axis to this, this is W0 plus W1 x1 plus W2 x2 plus W3 x3. So I'll get a plane out of that. So how to draw that plane? Let me show you that. I hope the code window is still visible. So if I show you this, so this is for the 3D matplotlib. I'm giving this normal vector. This is pretty easy code. And plot figure at these subplots, add the x1 x2 values and get x1 x2 as mesh, and then find the x3 value from the equation and then plot the surface and plot the normal vector. You can see this is the surface and we have a normal vector on this. Okay, I hope you are able to see it. So this is how you can do it for surfaces, but beyond this we cannot derive, we cannot imagine in 4D 5D because this is the limit. We can maybe only do the planes. Yes, question.
Sir, ये जो
So now I showed you that how to plot surfaces also. So the equation it pretty much remains the same, but beyond this we cannot imagine it. But the mathematics gives the tools to compute all these things. So you just have to give me normal vector. I'll give you the plane or the hyperplane. Okay. Now we'll see some decision boundaries. We'll see how to compute those decision boundaries. Let's suppose. Let me just plot some points. So I'm pasting a code over here, and I'll explain this code. So over here, what I'm doing is I'm generating some random points. I'm saying let's suppose these points belong to class 1 and these points belong to class 2. Okay, I'm generating some points over here. Okay, with the random C so that you can reproduce it. And then I am defining slope and intercept. I'm just defining a line. Okay, this is my line of separation, and I know the answer upfront. That's why I have given the hardcore values for slope and intercept. This is basically my W. The x values, I'm generating x values, and these are my y values. So this is my line basically. Okay, this is my line. So this is y is equal to mx plus c. Okay, now I am calling a scatter plot on this class, on the class of points. So we have this class, and then I'm saying class label 1, and we have this scatter plot for class label 2. Okay, and after that I'm plotting this. Let's suppose I won't plot this for if you see these are the points. Now you can clearly see that if I draw a line like this, if I draw a line like this, so I can clearly identify them. I can clearly identify which class it is. So I can draw a line like this, let's suppose something like this. Okay, with some errors. So there will be some errors, but I think most of the points I'll get right. So here the red region, let's suppose, or my positive class, and this is my negative class. So you can clearly see that if I draw a line, I can make a separation between them. Consider each of these dots a data point. Consider it is an image, vectorized image. It can be an audio. It can be anything. Consider it a data point. So now you can clearly see that class 1 and class 2, they have some separation. So they are linearly separable. If I just plot a line, so they'll be separable. But what I have done is I have hard coded in such a way so that I know the values for these lines. I know the value of slope and the intercept. So these are my x and y values. So if I plot this now, so I can differentiate between class 1 and class 0, or class 1 and class 2. This is my separating line. Okay, it does make some errors, that's all right, but usually you will do this sort of thing. So you'll have data points, and if you have a classification problem where you have class A1, class 2, and you want to differentiate, and you can see that they are linearly separable. Okay, and you want to find this line. So in the line, what you actually want to find is that W0, W1 and W2. You want to find the normal vector. Is that clear? Okay, let's suppose we'll take another example where we can have decision boundary as let's suppose spheres, or maybe a circle or something like which we have seen. So you can again plot the same things. If you want to have sphere, circle, things like that, you can plot them. So let's say I'll again create some random data. Okay, this is my random data, class 1, class 2. Okay, and now this is my circle. This is my circle x, circle y. So these are my plots, and I don't want to plot this. I'll show you the data first. So you can see again there is some structure to the data. Okay, there is some structure. So if I can, let's suppose, encircle this one, if I can make a circle around this blue, and whatever is outside that circle will be red points. So how to create a circle? You know the equation of a circle. So I have the center and the radius, and I have the theta with me. Okay, and this is how I can create x and y of this. And we have seen all the equations for circle, paraboloid. We have seen sphere equations. All these equations, just you need to code it and you need to find it. You can see it like this. So just if I uncomment this plot now, it won't be accurate because these are hard coded values. So you can see this, but most of the points are in the blue region over here. And what is the outside are the most the red with an error rate. But I just showed you these are decision boundaries. So I can just code these decision boundaries like this. Okay, and there are a lot of decision boundaries that we saw. With this, we have sort of covered the thing that I wanted to cover for the previous 3 lectures. Again, the same thing, motivation was if you know something in the theory, how to code it, and the second thing is how to visualize those things and how to see that mathematics actually works. It's not that somebody has just written symbols and numbers. It was actually to show you that the math, how to translate mathematics in the computer language and then how to get results out of it. Okay, so I'll stop the recording and take the questions over here.